Hi guys, my name is Asad, and today we'll be starting with our first topic. First of all, I apologize. It took me some time to start making these videos. I was just occupied in a couple of things, but we will be starting from quite basics, and we'll be moving towards advanced topics like RAG or machine learning, artificial intelligence, Kubernetes, Docker, Linux, depends on which department of computer sciences, even some segments of electronics as well. But this all will be connecting towards like connecting with each other. But we will be starting with quite basics as you can say, how does computer exist? So this is actually our first topic. So a computer exists because you can say just human just discovered how to control physical changes and represent information using those changes. Combine simple operations into complex, store instructions, make a machine execute those instructions. So it's as simple as that. Or if you remember, we used to make a flow of this computer when we were back in school. So it's usually input, storage, processing, and output. In much other fancy definition, if I have to put, I can say a computer is just a physical machine that represent information using control states and automatically transform those states according to instructions. So when I talk about these states, I will dig much deeper what these states are. But for that to understand, you have to understand that it's basically a machine which is built on billions of microscopic electronic components called transistors. Here we will enter towards a little bit of electronics and like what transistors are. We will further discuss in some other topic about transistors as well, and I will touch some of interesting topics like MOSFETs. However, for now, just our basic understanding would be fine. That you can say a transistor is just a controllable device, electronic device, and from our digital computers perspective, it is mainly used as a switch, which can be in any of the two states. It can be on and off, or as we represent these two states as 0 and 1. But these are basically our interpretations. Inside a hardware, there are actual physical conditions like low voltage or high voltage, absence versus presence of an electrical charge, one magnetic direction versus another magnetic direction. This brings us to a two states logic. So physical systems contain electrical noise, temperature variation, signal loss, or you can say manufacturing imperfections. So it is much easier to distinguish between two broad conditions rather than 10 precise conditions. So for example, if you have a low voltage, which is V is equals to 0, and if you have a high voltage, which is V is equals to 1, the system does not depend on exact voltages, but the voltage, if it falls in the acceptable range of low or high, that's something it will pay attention to. Because of this, the binary systems are quite fast, reliable, easier to manufacture. It's quite, you can say, the basic of how everything connects. Now, talking about binary systems. So, binary values are based with bits. So, a single binary value is called a bit. A bit can be 0 or 1. There can only be two possibilities for it. If there are 2 bits, they can have 4 possibilities. If we have 3 bits, it can have 8 possibilities. So this brings us to a formula of 2 to the power of n. And if you have like 2 to the power of 1, it will have 2 possibilities. If example you have 2 to the power of 8, it will have 256 combinations. So by combining all these combinations, computer can give you letters, numbers, sound, images, videos, instructions, and even machine learning models. So But one thing to keep in mind, it's bits do not inherit any meaning by themselves. A binary pattern like 01000001 could represent different things based on how system interprets it. So under one interpretation, it represents a decimal. But and in another, if you go towards ASCII character, it can represent a letter A. So it totally depends on different interpretations, how basically bits are perceived. If I'm talking from a perspective of transistors, and if I take them to the logical perspectives, so a transistor just act as a controllable switch, like I said. But when they are connected together, they create logical gates, which are like I think the few common ones are like AND or XOR. So like we know about the AND states. Like if both things, both of the A or B will be 1 and 1, then we will only get the answer 1. Otherwise, if it will be 0 0, it will be 0. It will be 0 1, it will still be 0. 1 0, it will be still 0. Only when there are two ones over there, you will get the value 1. So there's one interesting thing I would like to mention over here. It's also one of my Instagram captions. It's like extraordinary complexity of anything. Extraordinary complexity can emerge from an enormous number of simple operations. So that's something to you can observe these things like in your daily life as well if when you start to focus. So let's get back to where we were discussing about the basics. So a complete computer basically requires both hardware and software over here. Okay, so our hardware is just the physical machinery, like you can say processor, memory, storage device, motherboard, keyboard, network interface, or wire and electronic circuits. But a hardware provides the physical ability to manipulate information, but a software is a organized information containing containing instructions and data. So example, you can say operating systems, applications, games, web browser, databases, Python programs, or even AI models. So software is basically not separate from the physical reality. This is a common confusion. They're not separate from the physical reality. When our software is stored, it actually physically exists as patterns in electrical charges, magnetic states, or optical media. So the distinction over here is that hardware is basically a physical mechanism, okay? And software is the organized pattern that tells the mechanism what to do. We can further talk about instructions because instructions are also a form of data. So this was like a major breakthrough in computing that was stored program concept. So in early machines, changing the task could require physical rewiring the machine or adjusting switches manually. In a stored program computer, data is stored in memory. Instructions are also stored in memory. The processor basically reads instructions from memory and the processor executes them one after another. So this means that the same physical machine can become a calculator, a music player, a database server, or an AI system. The hardware does not need to rebuild for every other task. Then it's just the instruction changes. So this is why a laptop can run thousands of different applications, like at a time. So we can further dig deeper by saying like what is even instruction. So I mean, for computer point of view, an instruction is just a binary pattern recognized by the processor. It's a binary pattern. So at the lowest level, the processor understands only its own machine instruction set. Conceptually, instructions may mean load value from memory, store a value from memory, add two values, compare two values, or jump to another instructions or perform a logical operation. So for example, a machine level sequence may conceptually mean load the numbers stored at one memory location, load another number, add them, store the result, and move to the next instruction. So the processor does not read English words such as add. I mean, the word English, the English word is for human understanding. The actual instruction is basically encoded as a binary pattern. Sorry. So, if I have to sum this up, we will get back towards our 10th standard computer sciences, where we learned all of this, that a simplified computer contains several major parts. Central processing unit, if you guys remember, of course, CPU. Main memory, which has RAM, and then we have a long-term storage, which is like an SSD or HDD storage, which stores informations more permanently as comparative to a random access memory, because if you guys remember, RAM stores programs and data currently being used. It's absolutely quite fast, but usually loses its content when electrical power is removed. So that was like the basic differentiation that we used to study. Also, it contains input devices. These can be keyboard, mouse, microphone, camera, network connection, sensors in today's world. Output devices like monitor, speakers, printers, network connections again, motors or actuators. So, and of course, communication pathways are like the basic things over here, that the components communicate through electrical connections, and communication systems often called buses. Simplified instructions may look like this: input, memory, CPU, and output. The storage and networking may also exchange information with memory and the CPU. So, I mean, that brings us to a main question, what happens when a computer is turned on? So when a computer is completely off, the CPU is not actively executing normal instructions. It's doing nothing over there. So when we when we press the on button, the power system supplies controlled electrical energy to the components. Okay, that's the first stage. Then what happens is that the CPU, it is designed to begin execution from a known location after being reset. So it does not randomly chooses where to start from. The third stage is the processor basically begins executing firmware. So firmware is low-level software stored in a non-volatile memory. So it's commonly associated with systems such as UEFI. It performed such tasks such as checking hardware, initializing memory, identifying storage devices, locating a bootable operating system. So after this moves towards a bootloader. So this is an interesting topic which I will cover in the topic of Linux when I will discuss about kernel and other stuff, packages, kernel and other things, and about Fedora and Ubuntu. But at the moment, you can just say a bootloader is just a small program which begins loading the operating system. So in the stage 5, basically, the kernel takes control of the fundamental resources. So processor time, memory, storage, devices, processors, permissions, etc. And in stage 6, then when we move towards over here, the operating system starts background services and displays the login screen or desktop. At this point, the machine appears ready, although there are several or millions or billions of operations that have already been taking place. So, I mean, you can say, or you can ask, doesn't computer get confused? So a computer works because every layer follows precisely defined rules. The processor has an instruction, kind of an architecture that defines which instruction exists, how instructions are encoded, which register exist, how memories exist, and what each operation does. And memory has these rules governing addresses, reading, writing, and timing. Similarly, operating system has rules as well, like processes, files, permission, devices, communication. Even programming languages define rules for syntax, data types, operations, functions, program structures. Uh, so the computer world works through layers of agreed contracts. A lower layer does not need to understand the purpose of the higher layer. It only performs its own defined responsibility. So that's the layer of the modern computer. You can say a useful mental model to imagine a computer is as a tower. Okay. So there is like the physics is the layer one. At the bottom are physical laws governing electricity, voltages, current, materials, magnetism, light, heat as well. Then in the layer 2, we got electronic devices like physical materials are engineered into transistors. We got capacitors, we got wires, we got memory cells. Then in the in the layer 3, sorry, we got our digital logics like electronic devices form like logic gates, adders, multiplexers, latches, and what was the other thing? Counters, yeah. So layer 4 then comes towards the computer architecture, which is CPU, registers, memory systems, instruction decoders, communication buses. Then we got our layer 5, which is machine instructions, the processor executing binary instructions basically. In layer 6, we got our operating system. So the operating system manages hardware and provides useful services. Then in layer 7, we got our programming languages and runtime systems. Languages such as Python, C, Java allow humans to express instruction more conveniently. And then in layer 8, we got our applications. Applications like browsers, spreadsheets, databases, games, development tools. And then in layer 9, we get towards our distributed systems and cloud platforms. Like many computers works together through networks. And then layer 10, then we go towards our AI system, an AI model that runs on the same fundamental hardware, although they may like use specialized processors such as GPUs, but a complete chain, if I have to tell you, is physics, the first thing, then transistors, logic, CPU, machine code, operating systems, programs, and then AI. So artificial intelligence is not disconnected from basic computing. Okay, it is an extremely advanced arrangement built on the same foundation of physical states, binary representation, and mathematical operations. So, I mean, honestly, no single person can think about every transistor while writing a program. I mean, can you think of someone? Computing is possible because of abstraction. Abstraction just means hiding unnecessary lower level details while providing a simpler interface. Okay, for example, when you write a Python code, or let's not go towards Python code, but if you write total is equals to 7 plus 6, for example, you do not manually control transistor voltages over here, logic gates, processor register, instruction encoding, or memory timing. Or for example, if you say print hello world, just an example, you're not controlling anything over here. You get my point? The programming language and the computer system handle those lower layers. So an abstraction chain may also look like a, you can say from top to bottom, Python expression to Python interpreter, and then to the operating system services, then machine instruction, processor circuits, logic gates, transistors, electrical behavior. So each layer relies on the layer below it. This is perhaps the most important organizing principle for everything we will study. So, does the computer understand? A normal computer does not understand in any of the human sense. It does not inherently know what a photograph means, why a song is emotional, or why one number represents money, or why a document is important. It manipulates representations according to the rules. Even modern AI systems ultimately operates through encoded data, numerical parameters, or probability calculations, machine instructions, or electronic circuits, or metric operations. So an AI can produce behavior that appears highly intelligent, but physically still runs through ordinary computational mechanism. So questions about whether advanced AI genuinely understands are philosophical and scientific questions. However, at the hardware level, its execution remain computational, sorry. So if I have to say, if I have to give you a one complete example to sum up today's topic, it would be pressing a letter A, okay, in your system. So suppose you press the letter A key while using a text editor. The keyboard detects the physical key press, okay? Its internal circuitry produces an encoded signal. The signal travels through USB, Bluetooth, or another connection. The operating system's keyboard driver basically receives it. Then the operating system determines which key event occurred. The text editor receives the event. The text editor adds the character A to an internal documentation representation. A font rendering system calculates which pixels should display the character. And then the graphics system updates the required screen pixels. The display changes the physical state of those pixels, and your eye observes a shape A. So a simple key press therefore crosses multiple layers. I mean, I know this sounds so complex, but see, this is the beauty of basics. I mean, when you're learning things from the core, you will get to know, even though when we type so many things, our Microsoft Word, or on our text editor, in our VS Studio, or even on Microsoft spreadsheets or Microsoft Word, it's quite nice. I mean, I would say, if you get to know what's going down in the lower level. Of course, if you're working as a data engineer or data scientist or data analyst or DevOps engineer, you wouldn't really care about it. But it's nice to have that information if you are seeking such higher roles. I mean, I always say a good manager or a leader is the one who has a working knowledge of everything. Or even, okay, even if you don't have that complete working knowledge, it's good to have an understanding of everything. You should know what's the core basic and where it all began. So sorry, coming back to our topic. So like I said about this letter A simple key press, I mean, crosses so many multiple layers, so many confusing layers, honestly. So in other words, you can say mechanical, then electrical, then binary, then operating system, then application, then graphics, and then towards the light. So the computer does not contain a tiny physical letter. A traveling a tiny physical letter A, for example. I mean, it's not like A is traveling through any sort of wires or anything. It contains just changing representations of the letter at different layers. So to end our topic finally, I will go with the deepest answer I can give is like, how does a computer exist? So a computer exists as a hierarchy of physical and logical systems. Okay. So physical laws allows controllable electronic behavior, and then materials such as silicon allows transistors to be manufactured. Transistors now act as a, like I told, control switch. Then switches are combined into logical gates. These logical gates form arithmetic control and memory circuits. And these circuits forms processors and computer systems. Binary patterns represent data and instructions, like we discussed. And then the processor repeatedly fetches and executes these instructions. Operating systems organize the hardware, and the software uses those instructions or those services to perform useful tasks. Network connects multiple computers. An AI system use large amount of data and computation to learn numerical patterns. So the entire computer revolution is built on this basic principle that simple, reliable physical states can be organized into layers of increasingly complex meaning and behavior. So that's basically sum up from our lesson one. And if I have to give you a 4 or 5 liner notebook definition, I would probably say that a computer is just a programmable physical machine that represent data and instruction through controlled states. It's like it's literally like the first thing I said. And it stores processes, communicates that information according to precisely defined rules. So this ends our topic 1. In the topic 2, it will be, I don't know, I don't want you guys to get annoyed, but it will be much more basic. We will go towards what is electricity, and we'll go underneath the computer and examine what electrical charge, voltage, current, resistance, and power actually are. So see you in the next video. Thank you for watching this. Thank you. Bye.